Hello everyone. Let us continue a discussion on reinforced concrete design. We are in 11th week and this is our second lecture. In this week, we are going to learn the design of Intze tank, and in the first lecture we have already discussed the different components of Intze tank and what are the different stresses that we are going to consider when we design this structure. Now let us take a problem. So we have to design this tank here. As you can see, the basic geometry is shown here. So rise is 1.5 meter. The diameter of the tank is 8 meter. Then rise for the bottom dome is 1.2 meter. Then a diameter for this column is 8 meter. We have this conical slab whose height is 1.8 meter. And the side wall is having a height of 3 meter. So that's the geometry given, and then we have to consider the live load at the top of the dome as 1.5 kilonewton per meter square. So here live load for maintenance and other purposes. Then permissible stress of reinforcement is the tensile stress is 150 MPa. And we use M20 concrete and Fe 415 grade of steel. So with that, let us see how we can design the critical components for this Intze tank. So the first thing first, the roof dome here is the first critical component. And for that, let us provide a thickness TD of 150 millimeter. Now, if we provide that thickness, then we can calculate the dead load, which is 0.15 times 25 kilonewton per meter cube. So that provides dead load of 3.75 kilonewton per meter square. Then live load is already mentioned. So the total load is 5.25 kilonewton per meter square. Of course, we have to adapt appropriate factors, but for the time being, those load factors we are not going to consider. All of us, we can top up this with the appropriate load factors. Our main focus is not that. Our main focus is once this load is specified, then how to design this top dome, right? So for that, let us first find out the radius of the top dome. So we already have a rise of 1.5 meter, diameter of 8 meter, and then we can find out radius R1, as you can see here, that is from this level to this top ring beam. So here we have the expression, and we can find out the radius R as 6.08 meter. Now once we find out this radius R1 marked on your screen, we can find out sine of theta 1, which is in our case 0.658, and cos of theta 1, which is 0.753. So now let us see what are the different stresses acting on this roof dome. If you recall, we have already discussed the two main stresses acting on the roof dome is the meridional stress and hoop stress, right? And we also derived the expression for the meridional stress, as you can see here, T1. So it is omega times R1 divided by 1 plus cos theta. So you all know all these components. So if we put the values, we get the meridional thrust T1 is 18.21 kilonewton per meter. So from that, we can find out what is the meridional stress, and this time we have 0.121 Newton per millimeter square. Similarly, we can also find out the hoop stress. For that, sigma H is the stress component. For that, we have already evaluated the expression in the last class. So here is the expression, and in this expression, if we put all the values, we get a hoop stress of 0.038 Newton per millimeter square. Now remember, this is for theta 1. So for theta equal to 0, that is at the crown, we have a hoop stress of 0.106 Newton per millimeter square. Okay, so with those stresses, now let us design the roof dome. For that, you can see the stresses are very low. So sigma m is 0.121 and sigma h is 0.038. So sigma m is 0.121 Newton per millimeter square and sigma h is 0.038, and for theta equal to 0 it is 0.106. Now all three values, as you can see, they are very small, and that is the advantage of adopting this special type of geometry. Now because they are very small, we can provide the minimum amount of steel, which is 0.3% of the gross area along both the direction, as you can see on your screen, right? So AST in our case is 0.3% of the area. So we consider 1 meter wide area and the depth is 150. So the area of steel is 450 millimeter square. Now from this, if we adopt a diameter of 8 phi bar, we can find out the spacing, which is 111.11 millimeter. So we can adopt 110 millimeter spacing between two bars. So we have 8 phi at the rate of 110 center to center. Now let us design the ring beam at the top. So for that, again we have the hook tension. As you can see, hook tension is marked here, H1. So this is the horizontal component of the meridional thrust, T1. We have already evaluated, we already know theta 1. So we can find out these two components, H1 and V1. So the hook tension H1 is T1 cos theta 1. So we can find out that. So it is 13.71 kilonewton per meter. Now hook tension in the ring beam is H1 times D by 2. So it is effectively 51.54 kilonewton. Now next task is to find out the reinforcement in the top ring beam. So that we can easily find out. So it is there to resist the hook tension. So the value of hook tension divided by the allowable tensile stress, recall it was 150 Newton per millimeter square. So we can now find out AST, which is 356.6 millimeter square. So what we can do, we can provide 4 number of 12 phi bars at the top ring beam. So the area provided is 452, which is more than the area required, and therefore the design is okay. Now the size of the ring beam, for that let the size be A. So the equivalent concrete area we can find out using modular ratio. This expression is familiar to you. So we already have evaluated AST, we know M. So equivalent concrete area is this one, A plus 5424 millimeter square. Now limiting this tensile stress of equivalent concrete area to 1.2 Newton per millimeter square, we can easily find out the area of the beam required, which is 39,976 millimeter square. So we can provide 200 by 250 ring beam. So as you can see here, 200 width, 250 depth ring beam, and there are 4 12 phi bars. Now next component, which is the cylindrical wall. For that again, we have to evaluate the hook tension. Now there are hydrostatic pressure because of the water storage. So at the bottom of the wall, we can find out the hydrostatic pressure, which is 29.43 kilonewton per meter square. So if we consider a bottom of 1 meter strip of the wall, then we can find out the hook tension, which is PW times capital D by 2, and if we evaluate that, it is 117.72 kilonewton. So once we know the hoop tension, our task is to find out the reinforcement on the cylindrical wall, and that we can find out from the allowable tensile stress, which is 150 Newton per millimeter square. So AST in this case is 784.8 millimeter square. Now we can find out the spacing, and in this case it is 63.7 millimeter. Now this reinforcement will be provided near both faces. So over both the faces we have the reinforcement, which is will be 120 millimeter center to center of the sidewall, right? Now let us find out the tensile stress on equivalent concrete. For that, wall thickness, let us consider same as dome thickness earlier, it is 150 millimeter. Then tensile stress on equivalent concrete area, we already know TH, CL, and then from the equivalent concrete area we can find out the tensile stress, which is 0.74 Newton per millimeter square, and it is less than the allowable value of 1.2, and hence this is safe. So the compressive stress on this cylindrical wall, recall V1, this component V1, it is T1 sine theta 1, so it is 11.98 kilonewton. It is the load coming from the top dome, right? Recall here it was T or T1, its vertical component is coming from the top dome. Then we have the weight of the wall, 150 thickness, 3 meter high, 25 kilonewton per meter cube. So we have 11.25 kilonewton per meter. Then the top beam here, it will have its own weight. The beam is 200 by 250. So we can find out the weight of the beam, which is 1.25 kilonewton per meter. So the total vertical load per meter is 24.48 kilonewton per meter. Now the compressive stress we can easily find out from the geometry at this value of V2, which is 0.163 Newton per millimeter square. Now this compressive stress is low, and hence we provide the minimum of 0.3% of the gross area as the reinforcement. So AST is 450 millimeter square, and from this value of AST we can find out the spacing, which is 111.11 millimeter. Again, this reinforcement will be provided near both the faces. So let us provide 8 5-bar, each having a spacing of twice of this. So we provide 110 twice of that. So it is 200, as you can see here. Okay, let us go to the next critical component, and which is the bottom ring. So hoop tension in the bottom ring beam we have to calculate. So let T2 be the thrust per meter in the conical slab. So you can see here at the junction B, so at this point. Then if we resolve vertically and consider vertical equilibrium, so we can find out what is T2, because we already know V2. So it is 31.83 Newton per meter. So the horizontal component of T2, which is the hoop tension H2, is the cosine alpha. Alpha is this angle here. So T2 cosine alpha, and which is 20.4 kilonewton per meter. So the horizontal load will produce a hoop tension on the ring beam. So H2 we can calculate. Hoop tension due to H2 is H2 times D by 2, and it is 81.6 kilonewton. Now let the depth of the ring beam is 300. Recall at the top we had 200 by 250. Let us try with 300 millimeter deep beam. So water pressure on the ring beam, we can easily calculate. It is 8.83 kilonewton per meter. Hoop tension due to water pressure, it is this 8.83 into 8 by 2, which is 35.3 kilonewton. So total hoop tension is summation of this quantity and this quantity. So total hoop tension is 116.9 kilometer, right? And here you can see the estimation of this alpha and sine and cosine of alpha, which comes from the geometry. Now, reinforcement in bottom ring beam, we have to calculate. For that, we have already evaluated this total hoop tension, which is 116.9 kilonewton, as you can see here, divided by the allowable stress 150. So the steel required is 780 millimeter square. So what we can do, we can provide 4 number of 16 diameter bar, and the total AST provided is 804 millimeter square, which is more than the value of steel required. So that you can see here, ring beam dimension is 300 by 300, and then we have 4 16 fiber. Now, size of the ring beam, again we follow the same procedure. Let A millimeter square, and then equivalent concrete area you have to find out. In this case it is A plus 9648 millimeter square. We have to keep the limiting value of the tensile stress to 1.2 Newton per millimeter square. So from this we can find out the area. So that's the reason we provide 300 by 300. So we have adequate area provided for the ring beam, right? Okay. Next component, this conical slab, and it is designed for hoop tension and the bending. So for that, let us first find out the weight of the slab. So LCS, that is the length of the conical slab, we can find out from the geometry. It is 2.34 meter. Then this is the location of the CG. Now, thickness of the sloping slab, again let us provide 150 millimeter. So weight of the conical slab we can find out from this expression, and if you put all these values, we know all these components, and if you put that, we will get 179.2 kilonewton. So we have to design against hoop tension. Hoop tension on the conical slab is given by this expression, and that we are going to find in a minute. So what we have is the weight of the water on the conical slab. So weight of the water, again we can find out from the geometry, and as you can see here, the total weight on the conical slab due to water is 1117.8 kilonewton. So now we have to use this expression of hoop tension. We have already evaluated all the subcomponents. So now we can calculate the hoop tension on the conical slab, which is TH, CS. And if you put all these estimated parameters, we get hoop tension is 419.9. So 420 kilonewton. Now we have to find out the area requirement for the reinforcement, and that we get from the allowable stress, which is 150 Newton per millimeter square. So the area of steel required is 2800 millimeter square. So we can provide 16 numbers of 16 fibers, as you can see in this conical slab. So this 16 number will be provided on both faces. So each face will get 8 numbers of 16 fibers. So AST provided is 3216 millimeter square, while the requirement is 2800 millimeter square. So that is adequate. Okay, so now we have to design it against bending moment because this part of the structure will experience bending moment while supporting this weight of the water. So load per meter width of the conical slab we have found out here. So that is 63.5 kilonewton. So you can find out maximum bending moment, which is WCS times 1.5. 1.5 is this dimension, as you can see, by 8 is 12 kilonewton meter, right? So bending moment due to thrust, the axial component per meter due to thrust T2, we have already evaluated. So it is 31.83 kilonewton. Now provide 16 diameter bars with a clear cover of 25 millimeter. So effective depth we have to calculate total thickness minus the clear cover minus half of the diameter of the steel, that is effective depth, which is 117 millimeter. And distance between center of section to the center of steel, which is 42 millimeter. So resulting bending moment we can calculate, which is here 13.34 into 10 to the power 6 Newton millimeter. Now we have to provide the reinforcement for this bending moment, and that we can easily do. If you recall, this is the expression AST is equal to M1, which we have already evaluated here, 13.34 into 10 to the power 6 Newton millimeter divided by sigma ST, which is 150 times J times DCS. DCS we have evaluated, which is 117 millimeter. And J for this material combination is 0.87. So we have AST as 873.7 millimeter square. Now if we provide 12 phi bars, the spacing is 129.3 millimeters. So we can provide 12 phi diameter bars at 120 center to center in the outer face of the conical. Okay. Here is the estimation of J. If you recall, this we used earlier also. Now reinforcement at the inner face. So inner face of the conical slab, we provide minimum of 0.3%. And that area you can calculate, which is 450, and then accordingly the spacing is 174.4. So we can provide 10 millimeter diameter bars at the rate of 150 center to center at the inner face of the slab. As you can see here, we have two different type of bar. Outer face we have 12 phi at the rate 120 center to center, and inner face we have 10 phi at the rate 150 center to center, while the other direction we have 16 phi bar on each face. Now we have to design the bottom dome. For that, again, we already know the rise for the bottom dome is 1.25 meter, which is already specified. Span D2, again it is specified, which is 5 meter. So R radius we can find out R2 actually here. So for this bottom dome, which is 3.125 meter. The same way we did for the top dome, we repeat the same exercise. Now from the geometry we can evaluate theta 2, and from that we can calculate sine of theta 2 and cosine of theta 2. Sine of theta 2 is 0.8 and cosine of theta 2 is 0.6. Now weight of the water, because over the bottom dome the weight of the water will come, and for that you can see this dotted line, this much of weight of the water will come over this bottom dome, and that we have estimated here, which is 794.1 kilonewton. Now area of the dome is evaluated here, twice pi R2 times H2, that is the radius of the bottom dome and the rise of the bottom dome. So it is 24.5 meter square. So the load intensity, we can divide this load divided by the area. So we get the load intensity, which is 32.4 kilonewton per meter square. Now let us provide a thickness of 150 millimeter for the bottom dome. So the dead load for the bottom dome is 3.75 kilonewton per meter square. So the total dead load is the summation of this one we have evaluated plus the dead weight of the bottom dome. So which is Together, it is going to offer 36.15 kilonewton per meter square of load. Then again, for this bottom dome, we find out meridional thrust, T3. Same expression we used earlier for the top dome, and here it is 70.6 kilonewton per meter. So, meridional stress sigma m is 70.6 divided by B is 1 meter. And then we have 150 millimeter thickness. So, the stress is 0.47 Newton per millimeter square. Next is hoop stress. Same expression we used earlier also for the top dome, sigma h. We can use this expression. So, for alpha equal to 0, sigma h, if we put all the expressions, we get as 0.376 Newton per millimeter square. So, for the reinforcement, again, these values of sigma m and sigma h, they are very low, and therefore we can provide 0.3% of the gross area. So, again, it is 450 millimeter square. So, the spacing for 8 bar is 111.11. So, we can provide 8 bar at the rate of 110 center to center, and you can see these are the marked bars, and all of them will have the same spacing. So, now we are at the base of the bottom dome. So, this is the last critical component, the circular girder. For that, again, total weight on the circular girder. So, these are the components we have found out from the previous calculations. Recall, this part is the dead weight over the dead weight of water over the bottom dome, and this is the dead weight of the water over the conical slab. So, if we sum them up, we get the total weight of the water, then weight of the top dome and side wall, that is here, weight of the conical wall, weight of the lower dome, all are estimated here, and then weight of the circular girder. So, we provide a circular girder of 350 by 550, and for that again the total weight is estimated. So, the total tank weight here is 2873.9 kilonewton. Again, I repeat, for actual design we can adapt appropriate factors if necessary, then accordingly we can design. Now, bending moment for the circular girder, we provide number of columns 6, that is NC equal to 6. Recall, in the previous lecture I showed you a table where for a given value of NC we can find out C1, C2, C3. So, this is from the table, and they are used to find out maximum bending moment, maximum negative bending moment, maximum positive bending moment, and maximum torsion. So, here are the expressions of C1, C2, C3 are used, and then the respective values of maximum moments are 102.7 kilonewton meter, then 53.9 kilonewton meter, and the torsion we have 10.8 kilonewton meter. So, the depth of the circular girder, so we have 6 columns. So, we use this expression for evaluating the depth of the girder. Again, this is the expression earlier also we used, and the depth of the girder is 496.6. We have already provided 50 millimeter of girder. So, if we assume 40 millimeter of effective cover, so effective depth is 550 minus 40, which is 510. Now again, the steel we use here is Fe415. For that, we know the allowable tensile stress, and we can find out Kc and J. J is 0.87. So the modular ratio also we can find out, which is 280 by 3 sigma CBC. So sigma CBC is 7.2 Newton per millimeter square. Then longitudinal reinforcement for support moment of the girder. So Here is the expression. So the total support moment we have 119 kilonewton meter. So area of steel required, again we can find out. Here is the expression, and the area of the steel required is 1788 millimeter square. So what we can do, we can provide 6 number of 25 bars at the top side of the support section in the circular girder. So area provided is 1885 millimeter square as opposed to the requirement of 1788 millimeter square. So here is the detailing. 350 by 550 is the beam size, and then we have 6 number of 25 bars placed here. Okay. Now we have to provide longitudinal reinforcement for positive moment. Adopt the same approach. We have already evaluated positive moment divided by sigma st times j times d CG. All of them, these values we have found out. So we can get the area of steel required, which is 810. So we provide 2 numbers 25 bars and 2 numbers 16.5 bars at the bottom side of the circular girder. So area of steel provided is 1030 millimeter square, which is greater than the AST required. So you can see here is the steel provided at the bottom, and then shear stress for the circular girder. Shear stress we calculate VCG is equal to WT by 2 times NC. So here is the value of the shear force at the support. So equivalent shear force we get it from this expression, which is 288.9 kilonewton, and then equivalent nominal shear stress first we calculate, which is 1.62 Newton per millimeter square. So transverse requirement for the circular slab, you can see the distance between the center of the corner bars parallel to the width B1, you first find out, which is 350 minus 2 into 40, that is 270 millimeter. So the distance between the center of corner bars parallel to the depth D1 is equal to 550, this other side, minus 2 into 40, which is 470. So the area of the stirrup, we get it from this expression. So we provide 4-legged 10 millimeter diameter stirrups. So ASV provided is 4 times the area of each stirrup. So total is 314 millimeter square. So this is equal to the expression here. So we can find out SV. SV is 314 divided by 1.93, so which is 162.7. So we provide 4-legged 10-5 stirrup at the rate 150 center to center, and which are marked here. Right. So you can see the main bars and the stirrup. Now thrust from the conical slab to the circular girder, that as you can see here. So now weight of the water on the conical slab, this we have already evaluated. Weight of the conical slab is 179.2. Weight of the top dome and side wall, which is 615.25 kilonewton. So the total load is 1912.25 kilonewton. So T4 is the thrust exerted by the conical slab in girder. So we get this from this expression. So T4 is 158.3 kilonewton, right? Now the hoop stress in the girder. So horizontal component of T4. So T4 cos alpha, we already know the value of cos alpha. So we can find out H4, which is the T4 cos alpha, that is the hoop stress force, and then we will see the stress. So it is 101.5 kilonewton. Then horizontal component of T3, all are marked here. So T3 is coming from the bottom dome, and cosine component of that is acting, which is 42.4 kilonewton. So the net horizontal force we can find out from these two, it is 59.1 kilonewton. So the hoof force on the girder is HCG that we have evaluated here times d2 by 2, which is actually 147.75 kilonewton. So hoop stress we can calculate, it is 0.83 Newton per millimeter square, right? So we have that hoop stress. Now, once you design all these critical components, next is the design of column, right? So for the design of column, again, we have to consider the vertical load, we have to consider the bending moment due to wind load. Wind load calculation is not covered here. However, the lateral wind loads we can estimate from the respective code of the wind load, and then we can find out the bending moment. So there are 6 columns. Vertical load on each column we can calculate. So we can provide 400 millimeter diameter bars. Of course, we have to go for a very detailed calculation, but just to give you the idea how to continue for the column design, is that we first find out the total vertical load and moment, and that will come, the moment will come from the wind load analysis, and accordingly we can design the column, which is again discussed earlier. So you can adapt that. The only additional thing is wind load estimation. Okay. Now, if we see the detailing of this Intze tank, here is the complete structural detailing. So we start from the top dome. We can see the steel here, then first ring beam at the top, then cylindrical wall, then bottom ring beam, conical slab, and then bottom dome, and then finally the girder. Right. So that completes the design. Beyond that, we have to design the column and also the foundation. Okay. That you can adapt the similar procedure what we discussed earlier. So from this, you see how each and every critical component of the Intze tank is designed. The only thing is, again, for the column, the criticality is to consider the wind load, that separately we have to consider. Otherwise, the design of Intze tank is not that difficult. You can easily follow the steps that is discussed in this lecture, and then you can follow the design procedure and the detailing also. Now, crack width for a water retaining structure like this Intze tank is very critical. So we have to provide a watertight container with significant amount of durability, and for that again the provision we followed is IS 3370. Permissible crack width is 0.2 millimeter. So which is achieved by limiting steel stress, providing adequate reinforcement, and using smaller bar spacing. Okay, so this is a water retaining structure. That's why we have to keep this crack width as small as possible. Okay, and the critical components, so for the tension is concerned, is the cylindrical wall, conical slab, and the ring beam, right? And we have already discussed the detailing for these critical components. So follow all these design steps, and if you have any doubt, do let us know. We will clear your doubts. Thank you very much.